All right, I wanted to look at some of the stable forms of matter which can be formed from, now these are hadrons. Remember, hadrons are either mesons or baryons, where the baryons you can see over on the right column are 3 quarks per baryon. So these are the heavier particles. We see the proton and the neutron, which are first generation, and then we see ones that involve the strange quark. And it turns out that most of the particles that you see there do not involve the charmed, the top, or the bottom quark. The only exception is that bottom one, which has a charmed quark in it. But the rest of these here that are higher generation stable particles are what are called strange matter, because they have strange quarks mixed in with a combination of either up and or down quarks. Okay, and so under exotic conditions, this strange matter can be generated inside of a neutron star. It's thought that in the center of a neutron star, which has a density something like 1 billion times the density of water, you could take a little tiny marble, and if it were made out of neutron star material, it would weigh as much as the entire Empire State Building. Okay, and so this essentially is material that has nuclear densities. It's 100,000 times essentially more dense than the size of an atom. And in the center of a neutron star, there's some speculation that we might have strange matter. Because of the intense temperatures and pressures that are exerted there. And so we could have something like that sigma particle. You could have an up-down strange, or you could have a up-up strange, etc. This kind of strange matter can exist under these conditions. And it's thought that if this neutron star were to collide with another object and the strange matter could be released, that strange matter could start interacting with other matter and in a zombie-like fashion could create strange matter wherever it went. And so we're not sure whether this is true or not, but if it's released, we might have a zombie-like attack on all the rest of the matter in the universe. And so if this were to spread out from some initial location, you could eventually have the whole universe converted into strange matter. I'm not sure whether this is really possible because, well, we haven't perhaps been exposed to these kind of exotic conditions where a neutron star is torn apart so that the strange matter could be released. You'd have to have a mechanism for distributing the strange matter, but once it took hold, it could basically wreck your whole day, because if your matter were turned to strange matter, all the properties of matter in your body would be changed, and it would essentially destroy the whole universe. So this is an interesting possibility that I thought I'd just throw out there. There may be some technical problems with this, but this is a theory that's been proposed, is that strange matter could, in a zombie-like fashion, contaminate and convert the whole universe into strange matter if it could be distributed properly. Okay, so matter then that has strange quarks, so typically then most excited forms of matter contain up quarks, down quarks, and strange quarks, but not the charmed quark, the top quark, or the bottom quark. Now these quarks do exist, but they're unstable. Okay, so it's part of our scheme for understanding the different generations of matter, but it's not our scheme for understanding the kinds of particles that can exist in the universe under highly energetic conditions. And so those are the main subjects that I wanted to discuss with respect to the strong interaction. And of course, if you have questions regarding any of this, I hope you'll feel free to contact me and I can give you more information during an office hour. But what I'd like to do next is look at the weak interaction. Okay, so what does a weak interaction do? Well, this one's a little more subtle. Most of the other what we call forces of nature actually do produce a well-defined force which can act on things, whereas the weak interaction is more of a relationship between particles and is responsible for radioactive decay. And so that's important. Okay, so a typical example then of the weak interaction is going to be a neutron turning into a proton plus an electron plus an antineutrino. Anti-electron neutrino. This is one of our most classic versions of radioactive decay. And it's one of the simplest ones to understand in terms of trying to understand what's going on with a weak interaction. Now, Richard Feynman came up with this idea of Feynman diagrams and greatly simplified a lot of the calculations that are associated with what's called quantum electrodynamics and also quantum chromodynamics. And it's Feynman that realized that he can greatly simplify his figures if he defines an antiparticle as being a positive matter particle moving backward in time. Now, this doesn't necessarily mean that this is true, but it works in his Feynman diagrams. Now, what exactly that means in terms of a real physical interpretation is unknown. We don't know whether that is just a great mathematical trick that gives you the right answer, or whether there's some symmetry in time that relates to antimatter that we're we're not so clear about. But mathematically, they're considered to be the same. And so we could say then that this reaction then, where a neutron decays into a proton like this and produces an electron and an antineutrino is equivalent to this reaction here. And this one is easier to follow, even though it may not obviously be the same thing as this. We think of a neutron as interacting with a positive matter neutrino from the past, basically, and then it exchanges a, what we call here, a W minus particle. So this is the process then of radioactive decay. This is the mechanism of the weak force. Then, in the neutron, sending this W particle, this W minus particle, over to the neutrino, that'll turn the neutrino into an electron, and the neutron will turn into a proton. Okay, so in other words, the weak interaction then has an effect on both the strong force and the force that connects it into the leptons. Okay, and so it interacts in such a way as to change quark type, right? Because here we've got something that's 2 downs and an up. Here we've got something that's 2 ups and a down. So it's basically changed a down quark into an up quark. But in the process of doing that, a down quark turning into an up quark is equivalent to, well, you're going from plus 2/3 to minus 1/3. So that's a change in charge of -1. And so that -1 then is associated with a W particle having a, well, this is 2 ups and a down. So this would be let's see, you'd have to, here, you would need to be taking away a down and an anti-up. So here we have an up and an anti-up that would be produced by the uncertainty principle. The anti-up would go into the W minus particle, but the down would also go in to that particle. And so with the anti-up and the down being sent away, that leaves you with a net charge of -1 to be delivered to the neutrino to turn it into an electron. And then, because we've taken away an anti-up, then we're left behind with an extra up, and we also sent away one of the downs. So there we go. Got 2 ups and a down. Okay, now this weak interaction then is associated with the exchange of a very massive exchange particle called the W particle. There's also the W plus, and so that would happen then if a proton was interacting with a neutrino to produce a antimatter, a neutron, and then here this would be producing a positron. Okay. And also the Z particle. And so the Z particle then would occur if we had no net change in the type of baryon in the process of the decay. Okay? And so the important thing to get out of this is that with a very massive exchange particle, must be very short range. And so if it's short range, then we're talking here maybe on the order of 10 to the minus 17 meters, which is 0.01 Fermi meters. Okay, so we're, or femtometer. So it's just 1/100th of a femtometer. And so, but this basically then is doing is it's causing the beta decay in the nucleus, okay, by means of an exchange of a very massive particle, but only over a very short distance. Because here we've got delta E very big, because this is mc squared times delta T is very small, approximately equal to h bar. And so that means that the range here is delta x very small over c. And so that means that the delta x can only be on the order of like 10 to the minus 17 meters. And so because it has to happen over such a short distance within the nucleus, it doesn't, not highly probable that it'll happen. And so that's why it's called a weak force, because it doesn't really happen that often because of the very, very short range that's associated with being able to get a bullseye shot that causes this interaction to take place. Okay, but what's interesting about the weak force, other than that it's responsible for beta decay in the nucleus, as well as in free space, is that it's a relative of the electromagnetic force. So in other words, the kinds of symmetries that are necessary to produce this kind of an interaction fit into the same mathematical scheme as the interactions that, say, allow a proton to interact with another proton by means of a photon. So when we do the kinds of mathematical analyses of, and we'll talk more about symmetries soon, okay, so that we can get a better feeling for what is fully entailed by this whole idea of symmetry. But it just turns out that the math of how they fit together is so close that they're considered to be aspects of the same force. Even though it doesn't seem like it here. Mathematically, when you do more analysis, it turns out that that's the case. The problem, though, is that the photon essentially has zero mass. Okay? And so that means that the electromagnetic interaction could have infinite range. Because with zero mass, a photon always travels the speed of light. So that means that from the photon's point of view, the whole universe is contracted to zero length. So this is associated with infinite range. Even though we're borrowing energy from the vacuum to create the virtual photon, and we have to pay it back, it's called the zero-time particle. It takes zero time for a photon from its own point of view to cross the whole universe. Why? Because the universe's length contracted to 0 from the photon's point of view. So from our point of view, if we're looking at a photon, it looks like maybe it takes 100 billion years to travel across the whole universe. But from its own point of view, it takes 0 time. And so that's the reason why it doesn't need to be in a hurry to pay back the energy, because it takes 0 time to cross the whole universe. And so that's quite a bit different then than the weak force. The weak force has the shortest range of all. It's only 10 to the minus 17 meters. And so that is associated then with the fact that it has massive exchange particles. So this got scientists kind of concerned, because if the electromagnetic force is an aspect of the weak interaction, then why do the W particles have mass and the photon doesn't have mass? So this was a big problem that they were trying to solve back in the 60s. Why do the Z and W particles have mass if they're so closely related to the electromagnetic force and the photon doesn't have mass? So to solve the mass problem, several scientists came up with this idea of the Higgs field. So the Higgs field then would be the mechanism by which we could give the Z and the W particles mass. So the Higgs field then could interact with some particles more than others. Giving them more mass. The more the interaction, the more mass it would have. So this is kind of a wild idea, but and it's hard to explain. But this one guy won an award for explaining it in a way that was considered to be more clear than others. So let's just look at an analogy here. Let's say this was when President Obama is our president. Let's say that Obama is moving through a crowd of people. These are all reporters. So he's trying to get through. But all the reporters are swarming around him, and they're asking a bunch of questions. And so he's trying to push his way through. And so he's feeling sluggish because Obama has more interaction with the reporter field. But then here I am. I was walking nearby to Obama, and nobody pays any attention to me, so I just walk right on through. Okay, and so nobody cares about me. So this is like I'm like the photon, the little lonely photon, and Obama is like the big, massive Z and W particles. there's no interaction with the Higgs field, that means there's no mass. And so this is like the photon, light speed particle. But because Obama has more interaction with the reporter field, this interaction makes his inertia greater. So he's trying to push his way through. It's like trying to swim through molasses, you know. So the mass increases with increasing interaction. So as proposed, at the beginning of the universe, when everything was super hot, the Higgs field wasn't as strong. And so the Higgs field started acting as the universe cooled. And this is, although this is sounding like a long time has gone by, this is just maybe in the first second after the Big Bang. So at first, the idea then is that the photon had equal status with the Z and the W particles until the tiniest fraction of a second after the Big Bang, and at that point the Higgs field started becoming more prominent, started affecting the Z and the W particles more than the photon. And so those two forces then split off and became separate forces that were associated then with this Higgs field. So that was the idea. And then, in the Large Hadron Collider, they're able to generate energies with these protons that are moving around in opposite directions and then slamming into each other. They're able to get energies that were equivalent to the energies that were happening in the first second after the Big Bang. And they were able to discover the Higgs boson, the Higgs particle. And so this was a spectacular verification of something which, as you can see here, started out very theoretical, and but then was proven back in 2013. They finally announced their findings to the world, and at that point there was like 4 standard deviation worth of assuredness that they had the right answer. So the odds of it being wrong based on the assumptions that they had was just like something like 1 chance in 4 million. That was a statistical fluke. And at that point they were able to announce that they had discovered what basically gives particles their mass. And so this was a big step forward then in verifying the ideas of the weak interaction and how it fits in with the electromagnetic interaction, and also helps us understand more about the standard model, which we'll talk about next time.